Let's go to page 85 and talk about randomness. Randomness plays several important roles in the design of experiments. And hold on a second. Nope, it still didn't work. Having technical difficulties here. Well, we're having technical difficulties. Read those two paragraphs to determine whether you have random sampling and random assignment. Okay, randomization is very important in statistics. You are actually using randomness to your advantage. Randomness and variability are two of the key ideas. But randomness here, and so there are two key assignments, random assignment and random sampling. Random sampling involves drawing the sample for your study. Allows you to make unbiased inferences about the population based on the sampling. So in other words, random sampling is how you select the individuals from a population to participate. Now, once you have your sample, then you have random assignment. How do you assign people into two groups, the treatment group or the placebo group? Maybe even the male-female, although that's usually a little bit easier to do. So the assignments, you control and treatment groups in your experiment. Random assignment helps us to make causal conclusions about the data. So it's how you put them into groups. So the idea with random assignment is that it's combating confounding variables and competing explanations. It helps us to assume that the groups are as similar as possible before the treatment begins. Because if we have a lurking variable or a confounding variable, it's equally likely to apply to both. And so we can attribute to the differences just to that one particular treatment. So that's a key idea. So let's just have you talk to your neighbor about why random assignment helps mitigate confounding variables. So you get a couple minutes to do that, because this is a key point for why you do random assignment. You guys may need to yell at each other to connect.
It seems like we would never ever
If you're going to experiment.
like a random sample, you could probably get consistent in a random.
So, what would happen if I didn't use random assignment if I was going to form two groups? I might have bias. I might put like the healthier people into the group that I want to show there's a treatment, and I might put some there. And there's always implicit bias. And I know that this is the case that professors and instructors have a bias as far as calling on people. I could say that it's random, but it's not random because I generally call people in the back corners and not people in the front for some reason. All right, there's just some things that happen as far as this, and that's why sometimes randomization. So you want to use randomization so that you split it into the two groups as much as possible. So if you take a look at this, here you have random assignment, and the reason why you want random assignment is you can draw cause and effect conclusions. And then random sampling is to get a good, something that is generalizable. Okay, so if you select a random sample from one population, then they're randomly assigned, this in some sense is the ideal experiment. However, if you did random assignment that didn't do random sampling, for example, you just took this class, I took this class and randomly assigned you into two different groups. In some sense, this is unfortunately most experiments. I guess that is debatable. And the causal conclusion you can make is really only for the sample. A lot of psychology experiments are done on college students because they're right there and you're in academia and they're easy to get, and so you do some studies on those. So because of the situation, or you only take the data, within an institution and then do some kind of experiments. So you can only really conclude it for that particular group. The one up here, random samples are selecting from existing distinct populations. A lot of these are most observational studies. So you can still generalize this with the random sampling, but since you didn't have a random assignment, then you can't draw cause and effect conclusions from this. And then finally, who's ever available and you put them in there. This is just a bad observational study. So if you could go ahead and look at page 12 in your Saladron, how do I pronounce it? Course pack. Celadon.
Dr. Case, did you fill in that little blank for the selection?
No, just it's, I guess we could, couldn't we? This is just the selection of participants. Whereas random assignment is sort of the selection of treatment group. So back on page 12 in our course pack, we had talked about this earlier. When we had our definition of our proportion, number of people in our group over the population, that gives us our estimate for our population. Then we've already talked about indicator variables on Minitab. Like if you have like 5 categories, you can make 4 or 5 indicator variables where it's 1 in the group, 0 if you're not. But then we also talked about the control group and the treatment group. Control group generally gets the placebo. And then you want a double-blind experiment where neither the researcher nor the participant knows that they're being tested upon. So you can definitely, you're trying to restrict or rule out any other confounding variables, because maybe someone will try to help out the researchers by exercising or not taking their pills on time or something. So randomization is this random sampling and random selection. Replication is just a general idea from science. In science, if you're going to do an experiment, you would like to do what to replicate the results? Repeat it over and over again. So the larger your sample size, this kind of makes sense statistically, smaller your standard error, the more precise your results are, the better the results will be. Now, if you get too high, and DeVore makes this discussion, I don't really agree with DeVore, is that you can show there's statistically significant difference between two things. It's just meaningless. You know, we talked about going to Gas City, and I say it's 8 miles, and it's actually 8 miles, 100 yards. Is not really going to make that much of a difference in any kind of situation. But I could show it's statistically significant. It's just not practically significant. Blocking, on the other hand, is sort of stratification. So you break down your groups into smaller parts. So you may have a randomly selected population of humans, and then you might put them into like age groups, gender, or even in terms of work groups. So you might have like 9 blocks. You kind of vary in this, cutting down the variation for each of those in each of those parts, and essentially it's like stratification. So we'll write that there. This is like stratified sampling. Only instead you're going to do experiments on it. So Andrew, how could you assign people into your blocks?
Want to talk about spot it?
Sure. You just play the game Spot It, and then that will allow you to put them into various parts.
Yeah.
So you might have the soil, and you might put like 3 different fertilizers. You might have good soil, mediocre soil, or bad soil. You might have good fertilizer, bad fertilizer, and lethal fertilizer. And those could all kind of look to see whether your gardens grow Mary, Mary, quite contrary kind of thing. So, and just a reminder, in 2.1, you talked about randomization here as it relates to hypothesis and checking for independence and stuff. This whole idea of chance alone is the reason that we are looking at this, or why hypothesis testing plays such an important role. Let's go not to page 12, but let's go to page 86. Yes. One of the reasons why there was so much unrest in the 1960s was that there was a draft in the United States. Draft, go to Vietnam, get killed. I mean, that was kind of the big problem. And so in 1970, they were finding out that it was kind of unfair because people would go to college to get a military waiver. These are, of course, only men at that time. And so basically it was coming out that those Americans, or United States Americans, okay, there's more than Americans, but we'll just call them Americans, were generally less educated, came from poor communities, and there actually were several instances of insurrections almost in Vietnam just because it was kind of an unfair war. Listen to all the protest songs there. So in 1970, they instituted this lottery. They put these bins, and so you had your birthday, and then you had 366 balls. And they put them in this bin, and like rolled around like 2 times or 3 times, and they picked out a ball. Well, they looked at this correlation between these two. And it turned out the correlation coefficient was negative 2.226 between your birthday and the ball that it was when it was drawn. So you've got a lower, when your birthday was drawn at a lower amount, you were likely to be drafted. If you got a high number, then you were not likely to be drafted. So this was kind of a big deal because people's lives were online. And probably about every 2 or 3 years, there's some rumor that they're going to reinstate the draft, and then 18 and 19-year-old men get all hyped up and all this stuff. I think it's rather highly unlikely. I guess not impossible, but it would really, as shown in the 60s, a drafted military is a poor military. Anyway, that's. I guess that does relate to statistics, so I'm okay. I'm okay there. So the computer tells us that the sample correlation was negative 0.226. Is this too unlikely to happen by chance? Well, there are 2 possibilities. The lottery was random in a very unlikely outcome, or the lottery is biased, so that the outcome is about what we expect from such a lottery. So what would be our null hypothesis? That the lottery is random. Our alternative hypothesis is that it's biased. So we're not using any of the big 5 statistics. We're just kind of going through the process of how this might work out. Well, you calculate the p-value, and it's much, much less than 0.001. And so we would do what to the null hypothesis? Reject it. And because this is so far from zero, observe the 1970 lottery almost never occurred in random lottery. We have strong evidence that the 1970 lottery was rigged. It wasn't rigged; it was just biased. What happened was they didn't turn it enough. The balls didn't have enough chance to be randomly messed up. Okay. The one way that you can cheat at the state lottery, by the way, is that you get paint, and you paint some of the balls heavier, like 666. And so one time in Pennsylvania, the winning lottery was 666, and because of that number has some significance to people, people went crazy while they did some investigation, and it was the case that they had painted the balls a little bit heavier. There are other ways to cheat at the lottery that I will not state, but it was kind of rigged in that situation. If it had come out like 646, maybe no one would have noticed, but because it was 666, then people did. Okay, larger p-values, small p-values indicate strong evidence against the null hypothesis. Small, that's right, small. And you really need to know the sampling distribution when the null hypothesis is true. Let's skip ahead to page 89. We'll do some more thing on the previous pages. By the way, as you prepare for Tuesday's evening exam, I do encourage you to read through page 97 and 98 and 99 and 100. We're getting to the ideas of statistics, and just kind of keep reading those maybe every other day. You should be reading your Bible every day. Maybe this you can read every other day. And just kind of reiterate the points. For example, confidence intervals correspond to the 95% confidence intervals correspond to what? The method, yes, the method. The method is where the 95% comes into play. So let's just fill out this first one to kind of get the idea. Remember that, well, I'll just put it down here. For a confidence interval, we have our estimate plus and minus our multiplier times our standard error. That's the general form of the big five. And if you're looking at a z statistic or a t statistic, it's our statistics, our difference between our estimate and our null hypothesized value divided by the standard error. So let's just do the first one. You don't have to memorize the standard errors of all these, but it's good to kind of become familiar with that you've almost memorized them. So here we have the light blue sheet of section 8.2. So on the B side, you could take a look at this part right here. And the type of data is quantitative. A big assumption is a simple random sample, an SRS, or ID, and that we have normality. How do we check? Well, we check it through sampling protocol. And how do we check whether it's normal or not? Or, and so this is from the central limit theorem, or a probability plot. And we're not saying that it's coming from a normal distribution. We're saying it's coming from an approximately normal distribution. So you kind of look to see if the data all lines up on a straight line. The degrees of freedom. This is like extra part. Yes?
What is that after SRS assumptions?
Normality? Or this little thing that I drew out, crossed out. I was going to write IID, but simple random sample kind of captures that. Independent identically distributed data. It's kind of the same thing from that, but we'll just go with SRS.
What's above the central limit theorem?
N bigger than 30. Again, that's not set in stone. That's just what generally people accept. The degrees of freedom is n minus 1. Our statistic is t. Our estimating parameter, our statistic, is x bar. And we're estimating mu. So our test statistic is x bar minus mu naught over s over the square root of n. The standard error is s over the square root of n, and our multiplier is t star, maybe alpha over 2 n minus 1, depending on which way you're going on that. So we're just trying to see the connections between all these big 5, but then they're different as well. But generally for these big 5, estimate plus or minus your multiplier times your standard error, or your estimate minus the mean divided by the standard error. Later on we'll get some other more complicated, or not complicated, but different situations here. All right, what I'd like you to do then is just kind of touch base with your group and identify who your project manager is, because the project manager is going to play a very important role as far as getting people together during these busy and hectic times. Project, a lab, or a take-home.
Are we working in the same groups as take-home tests?
Take-home test number 2. Yeah. So Colin's not here. Okay, you're gonna go over to see Josh.
What were you saying?
Say that again. Oh, on number 7. Each person answers 9 questions. So if you have 3 people, you have person number 1, person number 2. You'll have 3 Yeah. You answer them on your own. I forgot about bonus points like that. I should have that, shouldn't I?
Yeah.
Okay. Which, Friday or Monday? All right. Not this one.
No, not this one.
I know.
Okay.
All right. Get the Lauren bonus 2 points if you turn it in by Monday at 4 p.m. on November, what is it? 23rd.
Turn it in a day or
I don't know.
So, again, this lab is supposed to help you prepare for the exam as well. So working on the exam, this lab is actually preparing for the exam too.
Probably on Sunday.